In this video, we'll see how the HOMO and LUMO orbitals of molecules can interact to get reactions to happen. This is why we're going to see diels-alder reactions happening as a 4+2 cycloaddition, as in a 4-pi system and a 2-pi system coming together to form a new molecule. And we'll also look at why we don't see this happening with another case, where we don't see 2+2 cycloadditions that function as diels-alder type reactions. When we do this, we remember that our diene is typically electron rich. We like to give it electron donating groups. And our dienophile is electron poor. Our ethylene usually has electron withdrawing groups. And we're going to see that if we take a look at the HOMO of the electron rich molecule and the LUMO, the unoccupied part of the electron poor molecule, we know that electrons are going from the electron rich to the electron poor. So we'll be using our highest energy electron rich electrons and our lowest energy empty orbital. And we're going to see here that the reason the diels-alder reaction works is because of orbital symmetry. Specifically, we're looking at the frontier orbitals, as in the HOMO and LUMO, and we see that the orbitals at the end of the molecule are arranged nicely. So the HOMO of butadiene has at the ends these two orbitals. Those correspond to these two orbitals, right? And if we go ahead and take a look at what's happening with the ethylene, we see here, we have in-phase overlap. The purples are lining up with the purples of the HOMO are lining up with the purples of the LUMO of the other molecule. And the greens of the HOMO line up with the greens of the other molecule's LUMO. And as a result, this reaction will proceed because of this overlap. The nice overlap allows the bonds to form. They're going to rehybridize because we're going to end up breaking the pi bond there. There's going to be a little bit of rotation happening, and we'll end up with our cyclohexene at the end of it. And so the diels-alder reaction works because of the overlap between the HOMO of your diene and the LUMO of your dienophile in a way that is symmetry allowed. So the symmetry of the orbitals allows them to overlap constructively, thereby forming new bonds. However, we don't see this happening. By the way, good time to pause the video and take a look at what's happening here. We don't see two ethylene molecules coming together. We don't see this happening to form a cyclic product. We don't see a 2+2 cycloaddition happening. Because if we consider their molecular orbitals, we need the HOMO of one and the LUMO of the other, right? The HOMO of ethylene has 0 nodes because there's only 2 electrons, 2 orbitals, 1 HOMO, 1 LUMO, 0 nodes and 1 node. If we try and put those together, now I realize I've got the colors and I've got them right, but could have drawn them earlier. Okay, anyways, we see here, I'm going to draw it upside down because why not? The point is that there's no nodes in the top molecule, 1 node in the bottom molecule. We have constructive overlap here between the two purples, but we do not have that present on the other side. And as a result, because that's a destructive interference, we don't see this happening. We're not going to form a cyclo product here. In fact, what we do see, if we were to try and do this, we would end up polymerizing ethylene. So we would just make a single bond between the purples, and we would end up having radicals now on the ends, which then we could add to more ethylenes. Should be single. And we can keep the chain going. They'll actually form polymers instead of cycloaddition products. But that's something for another day. The point is here that in terms of trying to do a thermal reaction with ethylene and ethylene, we do not end up getting a cyclic product because we don't have the correct symmetry. So this is what's called symmetry forbidden. So because the orbitals do not overlap constructively in all cases, we're not going to see symmetry allowing for this to happen. However, something interesting does happen if we were to instead use a different energy source. So heat normally allows for Diels-Alder to happen. It just makes the energy barriers, or it allows molecules to reach the energy barriers. And so in the next video, we'll take a look at some photochemical reactions using light instead to see what's going to happen, to see if we can't get these two ethylene molecules to form that cyclobutane. And we'll see that in the next video.